When it comes to multiplication with matrices, here is where we start to deviate from our standard scalar multiplication, where we just have single numbers. So first things first, when we take a matrix times a scalar like 5 times A, that's straightforward. We're just going to take the 5 and we're going to multiply every single element in A. So if this is my A, I would end up with 5 times 3 or 15, 5 times 10 or 50, negative 5 times 5, negative 25, and then keep going. 20, negative 20, 20. That's straightforward. When we do scalar multiplication, when the scalar is multiplied by a matrix, then we're just going to do it element by element, where we take the scalar, multiply it by all of the elements. And that's pretty straightforward. However, when we do a matrix times a matrix, that's where we're going to run into issues. It's going to be different from what we might think of intuitively. So if two matrices are multiplied by each other, the operation A times B, so A times B, can only be carried out if and only if the number of columns in matrix A is equal to the number of rows in matrix B. So here's an example of that. Let's say I have A, it's an m by n, illustrated here, and B is an n by p. It's just essentially they're just two matrices of different sizes. I can only multiply these two matrices together if these inner dimensions match. So this is typically how we would write it. We would say A is 3 by 3, B is 3 by 2. If those inner dimensions match, then I'm good. I can do multiplication. And my result is going to be another matrix, a new matrix, that's going to have the same rows as A and the same number of columns as B, or the outer dimensions here. So my result here is going to be an m by p. So if I look at this example over here, B here is a 3 by 2, C is a 2 by 3. So if I want to do B times C, I need to check first if this is even possible. B is a 3 by 2, C is a 2 by 3. These inner dimensions match. That's great. That means I can multiply B times C. My result, whatever I call it, is going to be the same size matrix as my outer dimensions, which in this instance is 3 by 3. So that means I can multiply B times C, and my result is going to be 3 by 3. One key property of matrix multiplication is that order matters. So here, this first one essentially states that order matters. So notice, if I do B times C, my result is a 3 by 3. However, if I do C times B, first I need to check if I can do this. C is a 2 by 3, B is a 3 by 2. Notice my inner dimensions match. That's great. I can do this multiplication. I will get a result. My result is going to be a matrix of my outer dimensions, or a 2 by 2. So B times C gives me a 3 by 3, but C times B gives me a 2 by 2. So first thing we need to do is check to see if we can actually do matrix multiplication. Once we figure out we can do matrix multiplication, then we are going to follow this step here in order to do that matrix multiplication. I am going to go over this in lecture with examples, but essentially what it means is we are going to apply the dot product over and over and over and over and over again, given the rows in A and the columns in B, or the rows in our first matrix and the columns in our second matrix. Keep in mind the dot product is something you've probably seen already in like physics. It's between two vectors. So the dot product is between two vectors of the same length, or the same size, the same number of elements. And in order to calculate the dot product, we're just going to take all of the elements in one vector, multiply them by the elements in a second vector, and sum them all up. So over here with these two vectors, A and B, A dot B is going to be these two numbers multiplied by each other, 9 times negative 2. These ones multiplied by each other, negative 10 times negative 1. These ones multiplied by each other, 6 times negative 1, and then I would add all of that up to give a single scalar value. So negative 18 plus 10 minus 6, where A dot B is negative 14. So make sure you guys know this process. Like I said, I will go over it in class, but this is essentially the key to doing matrix multiplication.